10.4 Use inscribed angles and polygons. Nice to have you along with me here. And our objective is I can use inscribed angles of circles. So write out your essential question and think about that as you do. How do I use inscribed angles? What does that term inscribed mean? And how do I use those inscribed angles of circles? So what is an inscribed angle? An inscribed angle is an angle whose vertex, remember that's the corner of your angle, the vertex is on a circle, and whose sides contain chords of the circle. So it contains these chords. Remember the chords are endpoints on the circle. In this case, that ray continues to go beyond the chord, but what they're saying is that the one ray, the one side of the angle, is inside of the triangle, or of the circle. So you might even want to circle the word in, or the prefix of in, and put inside. So when you think of inscribed, please think of inside of this circle. And specifically, you're looking for the vertex being on the circle. Vertex on. So that's the main clue there. And the arc that lies in the interior of the inscribed angle has endpoints on the angle, and that's called an intercepted arc of the angle. So interior should come to your mind when you see the word intercepted. Or think of it like football. Here comes this football cruising along, and it is intercepted by a defensive player. So where this angle intercepts the circle is called the intercepted arc. In the blue here, that is the intercepted arc for this inscribed angle. And over here, this is the intercepted arc for this yellow inscribed angle. And we have a theorem here that the measure of the inscribed angle is 1/2 the measure of its intercepted arc. So this inscribed angle, the measure of that inscribed angle, is 1/2 the measure of the intercepted arc. So if, for example, the intercepted arc is 80 degrees, then the inscribed angle is going to be 40 degrees. Now you'll remember when we did the central angle, that whose vertex is on the center, then the inscribed arc and the measure of the central angle are congruent. They're equal to each other. Congruent would not be the right word, because they're not the same shape, same size, but instead the measure of the intercepted arc and the central angle are equal to each other. Whereas the measure of the inscribed angle is 1/2 of the intercepted arc. And you'll see that over here, that if we have an intercepted arc of 140 degrees, then the inscribed angle is going to be 1/2 of that. Or if they started us off with the inscribed angle was 70, then you multiply that guy times 2, and that gives you your intercepted arc. And again, the central angle and the intercepted arc, those have the same measure to them. So with regard to inscribed angles, there are 3 different cases for that. Remember, always the vertex is on the circle. It's always going to be on the circle. But the center, where is the center in reference to the inscribed angle? Sometimes the center is on that inscribed angle. Other times the center is interior to the inscribed angle, and other times the center is exterior to that inscribed angle. Example number 1. Let's do this. So find the indicated measure in circle P. So here is circle P. They want us to find the measure of angle T. So angle T, that vertex is on the circle. So this is an inscribed angle. And here is the arc RS, is the the intercepted arc for this inscribed angle. And if the intercepted arc is 48 degrees, remember that the inscribed angle is half of that, so this angle is going to be 45. What am I saying? Going to be 24 degrees here. Then they're also asking us for the measure of arc QR. So we want to know the measure of this arc here. Well, we do know that this is an inscribed angle over here, and because that vertex is on the circle, and so therefore this intercepted arc of that inscribed angle will be double the inscribed angle. So this intercepted arc would be 100 degrees. The measure of that arc is 100 degrees. And we also see that this is the center. So this chord, TR, is a diameter because it goes through the center, and therefore that diameter creates a semicircle. This is 180 degrees, TQR, arc TQR. And so if we do that whole 180 degrees and then take away 100 degrees from this arc, then we are left with 80 degrees up here, and that's what they want us to find. Example number 2, the measure of arc RS, and we want to find that. Well, we do have, this is a intercepted arc here of this inscribed angle. I know it's an inscribed angle because the vertex falls on the circle, and therefore the intercepted arc is double the measure of the inscribed angle. So take that inscribed angle of 31 degrees, multiply it times 2, and that's going to give me 62 degrees. So the measure of this intercepted arc, or this arc here, is 62 degrees. And notice that this is also the intercepted arc for this inscribed angle, angle T. And so this angle T is also going to be 31 degrees, just like the other intercepted arc. That's interesting. In fact, that leads us to a theorem here, and this is in your, here it is in the bottom, right in the middle of your page here. If two inscribed angles of a circle intercept the same arc. So here are your two inscribed angles, and they come out and create this same intercepted arc of arc AB. Then the angles are congruent. Well, that makes sense because that's what we just did here, isn't it? That here these two inscribed angles both have the same intercepted arc, and those two inscribed angles are both congruent. And so this major portion of your notes, the front page here, we will do this in class, so please do not copy this down at this time, but let me explain what's being emphasized here. That here is a intercepted arc in the blue, looks more like purple, but that's blue, let's consider that to be blue. And here's a central angle that's of this intercepted arc. So that central angle, if we were to measure this one in particular, it's 86 degrees. And so therefore your intercepted arc is also going to be 86 degrees. And if I create this purple inscribed angle and measure this angle, it's going to be half of the central angle, half of the intercepted arc. So in this case it's going to be 43 degrees. But if I were to, as it were, drag this vertex down on the circle over here, and I could measure this angle, this inscribed angle, this also would be 43 degrees. And if I was to drag this vertex down over here, still having the same intercepted arc, then this angle also would be 43 degrees. So when it's an inscribed angle, it does not matter where that vertex is on the circle. If it has the same intercepted arc, then it's going to remain the same angle throughout. So that's emphasized in this theorem that you have here. Example number 3 in your book. Name two pairs of congruent angles in this figure. Well, let's look for common intercepted arcs. So here's arc JM, and notice that angle K is a inscribed angle that has this intercepted arc, and angle L also is an inscribed angle that has that same intercepted arc. So angles K and L are congruent to each other. And the same is true on the mirror side of it, that here is arc KL, and that is a intercepted arc in the inscribed angle J that comes out and intercepts the circle from K to L, and angle M also intercepts the circle from K to L. So therefore angles J and angle M are congruent to each other. In this guided practice, you have this in your notes. Do, though, maybe pause the video now and fill in, if you have a red marker or a pen or something, or maybe just with a pencil, make that more distinct. This is the red arc or angle that's talked about here. I wasn't able to make a color copy for you. So that's the red angle they're talking about. You want to find the measure of that red angle. Here you want to find the measure of this red arc, and here you want to find the measure of that red angle. So go ahead and pause the video and do that. Let's look over now at polygons. A polygon of an inscribed polygon. If all of its sides, let's start from the beginning. A polygon is an inscribed polygon if all of its vertices lie on a circle. So this is an inscribed polygon since all of its vertices lie on the circle. And this also is an inscribed polygon. In this particular case, it's an inscribed quadrilateral, because each of its vertices lie on the circle. So those are inscribed polygons. And the circle that contains the vertices is a circumscribed circle. So this circle circumscribes, or goes around. When you see circumscribed, think of circumference. Circum means to go around. So circumference is the distance around the circle. A circumscribed circle goes around that polygon. So this circle circumscribes this triangle over here. This circle circumscribes this quadrilateral. Here's another theorem. If a right triangle is inscribed, so here's your right triangle, and if that is inscribed in a circle, so again, when you see the word inscribed, you're thinking inside of the circle, or specifically the vertex, one of the vertices. Well, I guess if it says inscribed circle, inscribed in a circle, then it's referring to, like we said, all three of the vertices of that triangle are on the circle. If that's the case for a right triangle, then the hypotenuse, this hypotenuse across from your 90-degree angle, is a diameter of the circle. So why is that the case? Well, this is an inscribed angle, right? This 90-degree angle, and it creates this intercepted arc. Remember, the intercepted arc is always double the measure of your inscribed angle. So if the inscribed angle is 90, then the intercepted arc is 180 degrees. And if that arc is 180, therefore it's a semicircle, and therefore this is a diameter of the circle. And that's true anywhere that you would, say this way, if you were to move this vertex anywhere in the circle, it would still be 90 degrees, and if this was across a diameter like that. Conversely, if one of the sides of an inscribed triangle is a diameter, so if they start out with a diameter, and you create a triangle from another vertex that's on the circle, then this angle here, this inscribed angle, will always be 90 degrees. And let's go through this now. So here's a statue, and we want to take a picture of this entire statue, meaning not just the inside parts here, but also the frame of this statue. And our particular camera has a 90-degree view field, or field of vision, on it. And so we want to find all the places where we can set up our camera such that we will get the entire, be able to receive all and nothing but the full statue. So what we could do is, what we could do is measure this. We could consider this to be a diameter, right? Like we just talked about. That let's go in here. If we have a 90-degree view on the camera, then what's created is a diameter of a circle. So let's consider this to be your diameter. Let's measure the length of that, and then take half of that length and measure out that half of the length and find where the center of this circle would be, and then get a tape measure, or use that same tape measure and anchor it down at that center of your diameter, and then walk that tape measure in that arc as long as you're anchored and you're equidistant from that center. Each place along this circle is where you could set up your camera and adjust it such that within your field would be the entire statue and nothing but that statue. Pretty cool. So our last theorem here in this section, and I have this here in your notes. A quadrilateral can be inscribed in a circle. Here's a quadrilateral. Remember, inscribed means that all of the vertices of that polygon are inscribed on the circle, and that can be the case if and only if its opposite angles are supplementary. Its opposite angles need to be supplementary. I'm indicating that just by writing 100 and then putting arrows out to both of these. Of course, I'm not saying that each of these angles are 180 degrees. I'm saying that the sum of these two angles is 180 degrees, which would make them supplementary. So regardless to what kind of shape the thing is, so even if it's some other kind of funky shape, let me just throw down something real simple and easy. So here is another example of a quadrilateral. Okay. In fact, you have some in your book like this. I'm not sure why I'm doing this. But notice that this inscribed angle here includes your intercepted arc over here, and the opposite inscribed angle, let me draw that in blue, the opposite of this inscribed angle is going to create this intercepted arc. And obviously, add those two intercepted arcs together and you get 360 degrees, and you'll remember that your inscribed angle is half of the intercepted arc. So if the sum of the intercepted arcs is 360, then the sum of your two inscribed angles is going to be half of that, which is 180 degrees. Let's do these last two examples here, and then I'll cut you loose and be on your own. So here they want us to find the value of each of these variables, and so let's find the x first. And I see that these two, first of all, This is a quadrilateral, it has 4 sides, and this quadrilateral is inscribed in this circle because each of the vertices of this quadrilateral is on the circle. And I can connect these two opposite angles together, and we know that those, because it's an inscribed quadrilateral, therefore these two opposite angles are going to be supplementary. So we could say 80 plus x, and that's what they're saying here, 80 plus x equals 100. And then I could solve this equation, of course, by subtracting 80 from both sides, and so now x equals 100. Could do the same thing with these two opposite angles, that they're also going to be supplementary because these are opposite angles of an inscribed quadrilateral. So 75 plus y equals 180. So I subtract 75 from both sides and get y equals 150. For this next example, same exact principle, except we have more variables here. So to do the one with the a variable, these two opposite angles look similar to the one that I had drawn here. These two opposite angles in this inscribed quadrilateral are supplementary. So we can say 2a plus 2b, 2a plus 2a. They both have the same measure. In this case, happens to be that case. Not always will be the same measure. But that equals 180, and then you can add like terms and get 4a equals 180, and then divide both sides by 4 and get a equals 45. You can also do the same thing with these, with angles k and m, opposite angles of an inscribed quadrilateral, and 4b plus 2b equals 180. These guys are supplementary, so I can create that nice little equation. Add like terms, 6b equals 180, divide both sides by 6, and b equals 30. And in fact, that is a kite, isn't it? See that, this quadrilateral here? Because these opposite angles are 180 degrees, therefore, yep, this guy is going to be a kite. And so you could, they're symmetric on both sides. Pretty neat. Okay. The rest is on your own. Number 5 and number 6. Hope you can do that challenge. If not, go back and read the book more carefully. All right, look forward to seeing you in class soon. Bye-bye.